Uh, Good evening to all of you, and I'm Nandini Harinath, Deputy Director, taking care of spacecraft operations. Our area is called Spacecraft Operations Area in ISTRAC, Bangalore. ISTRAC is ISRO's telemetry tracking command network, and we take care of all the on-orbit satellites that are there in the low Earth orbit and in the deep space missions. Um, so today, first of all, let me thank the organizers for inviting me for this lecture. And I think I have about an hour. I'll try to stop around 5. My topic today was ground segment, ground stations, TTC network, command tracking, and management of satellites. So I'll try to give an overview of this topic today. This exactly the kind of work we do here in our area. So in my first slide, you get a glimpse of all the elements that are involved in spacecraft operations. Um, just to begin, this is from a humble beginning from the church from Tumba. I'm sure most of you know about how ISRO began its journey way back in 1963. We've come a long way. We've reached the farthest we've gone is our red planet, that is the Mars mission. And I was a part of the Mars mission, and have been proud of all the missions that we've accomplished so far. So yeah, so when I say ground segment, it involves number of entities. I think the most challenging thing about the ground segment operations is the number of entities it involves and the number of centers, not just your center, but we need to interface with agencies within ISRO and outside ISRO for us to carry out the operations. This is again just a glimpse of the kind of the interfaces we have with so many centers. It could be, you can see here the integration and the lab facilities in URSC. They are the mission designers, and we get all the spacecraft inputs from them. And we also interface with, of course, with Sriharikota for the launch purpose, wherein we get ready for the mission even while the satellite is on the launch pad. So our work starts right from that time, even before the liftoff. And you can see all other centers also, even those that are not there in the picture. We interface with all of them and to carry out the mission. So again, yeah, so, the ground segment, when you say it caters to various type of satellites and various type of requirements. It could be, the regular low Earth observation satellites. We have had a number of them in the last few years. Right now, we have about 25 satellites in our kitty, and we controlling all of them. Controlling and tracking, in the sense, also involves not just getting data from the satellite, analyzing the data, and uploading commands for the payload operations, maintaining the satellite health, taking care of any anomalies that might happen, contingency recovery that we call. And of late, we've had so much of space debris. Quite often nowadays, we also do collision avoidance maneuvers, in order to avoid getting hit by a defunct satellite or a space debris. And apart from that, the satellites also continuously experience drag, and they need to be maintained in their orbital slot. So orbit maneuvers is another very important type of operations that we carry out. And apart from that, we also carry out regular calibrations and for the payloads or for the mainframe systems. So, so I will be talking about all of this that I mentioned a little more in detail in my lecture today. But before that, we also have number of satellites in the geostationary orbit. We've gone to the moon. We had the Chandrayaan 1, Chandrayaan 2, Chandrayaan 3. The landing took place in the office that I'm right now sitting in. That's the control center that you all saw live on TV. And we also had the Mars orbiter mission for almost 8 years, though the intended life was only 6 months. The Mars orbiter mission survived for nearly 8 years, giving us very valuable data, not just in terms of payload, but in terms of enormous experience that we gained on how to manage, how to track and manage a satellite around the red planet. So again, going way back in time and looking at the kind of satellites we've all controlled so far, they could be, again, not just uh, uh, a function of the distance or the altitude. They're also a function of the kind of payloads they carry and the weight of the satellite. So we've flown and tracked microsatellites and nanosatellites weighing less than 15-20 kg. Some satellites are of the order of hundreds of kgs. And our Earth observation satellites generally are in the range of 600 to 1000 kg. So we've had number of types of satellites, and we've had them in various altitudes. So why I'm mentioning all this is different types of satellites, different types of orbits, different inclination, they impose different kind of requirements on the ground segment. And the ground segment has to equally cater to the space segment in terms of, newer technologies and newer applications that are present in the satellite. So here in the slide, you see that we've had small satellites. We had the Earth observation satellites are usually in the low Earth orbits in order to give us, good pictures, good resolution pictures. So we keep them in the low Earth orbit. We've also had the Navig constellation. I'm sure most of you here, students, have heard of Navig constellation, which is ISRO's own type of GPS mission, very innovatively put in geostationary and geosynchronous orbit to give us coverage all around our country, precisely to say 1500 kilometers around the country, uh, more than the borders. Apart from that, we've had our communication satellites. We've had our own share of interplanetary missions and science missions. So, the science missions also impose tremendous challenges on the ground segment and impose different kind of requirements on the ground segment in order to track them, in order to control them, and in order to manage them. So let me come to the core topic today, that is the mission operations. So what does mission operations involve? So most of you have seen the landing of the Chandrayaan. That is just one part of the mission operations we do. You've seen, I'm sure you've all seen the liftoff that takes place from Sriharikota for the launch vehicles. So the big difference between the operations of a launch vehicle and the satellite is that when you were looking at a launch vehicle liftoff, everything is autonomous. There's no man in loop at all, unless, of course, unfortunately, if there is an abort. Everything is autonomously done, and the team just monitors the data in order to get a post-flight, in order to carry out a post-flight analysis. But it's very different in terms of a satellite. So the satellite, the monitoring of the satellite and the commanding for the satellite starts right at the launch pad itself. So we call this activity as the launch pad initialization, wherein the satellite is initialized to favorable conditions in order to acquire its orbit and attitude and commission its systems quickly when it is in orbit. So the initialization takes place in the launch orbit. So for this, we have antennas in Sriharikota that, that receive data from the satellite. Uh, but otherwise, while the satellite is in orbit, the tracking is usually done with the help of our antennas. And ISTRAC has, I think, 45 antennas all around the world. So many of these satellites, they could be polar or inclined. And as the Earth rotates, the satellite will be passing different regions on the globe. And in order to get more and more data from the satellite, we need to have stations all around the globe. So that is part number one. So once you track the satellite and you get data, uh, the next important thing is the monitoring and control. So like I said, most of the satellite require day-to-day maintenance. So it could be for maneuvering the satellite to put it back in its orbital slot. It could be carrying out, turning on the cameras. If it's an Earth observation satellite, most of them carry either optical or radar cameras. So it could be to turn on the cameras over the desired region. So this activity could be once a week or sometimes once or on the previous day. And then there are some maintenance aspects on the satellite which require frequent commanding in order to keep the satellite healthy. So all this is done in the control center. So we call it health keeping of the satellite. And then apart from the commanding, there is a very critical analysis of the telemetry data that we get from the satellite. So the satellite also records the housekeeping or the health data when it is not visible to the ground station. And then whenever it is visible to a ground station, it will play back the older data so that we can construct the entire trajectory and we know the entire time, we know what is happening on the satellite. So this we call as playback and analysis of the data. And on a daily basis, we analyze all the health parameters of a satellite. You may be all be wondering, she's talking of housekeeping and health monitoring of the satellite. Approximately how many parameters are there on a satellite? And do you think the satellite has? So the satellite has various subsystems. It could be the control systems, it could be the actuators, sensors, thermal, power, the reaction control system or the propulsion system. So all these are the payloads. So all these the subsystems are monitored via parameters that are sent in the telemetry. And some big satellites can have as many as 6,000 parameters in order to understand how they are behaving. So so this is about monitoring and control. Let me go to the next box, that is flight dynamics. I'm going to be talking a little more about flight dynamics later, but the orbital dynamics for any satellite is extremely important to understand in order to track it. So in order to know the satellite's position and velocity when it is in space, you need to get the information either through the onboard GPS receiver that is there on the satellite, or we have something called ranging and Doppler. So we receive tracking data from the satellite. You can estimate the range from the time of arrival of the signal. You can estimate the Doppler, and from the change in the Doppler, you can estimate the velocity. So this range and Doppler also is one method to give us the information about where the satellite is at a particular instant. Of late, most of our satellites also carry GPS receivers. So even though it instantly tells you where the satellite is, in order to predict the position of the satellite at a future given point of time, we need to do something called orbit determination. So the orbit determination involves understanding where the satellite is and predicting the orbit for the future time. And this information needs to be dissipated to all the tracking ground stations which are all around the world. So the stations need to understand when the satellite is going to fly over their station, and what azimuth and elevation will the station be able to find that particular satellite. So there are a number of other uses for this flight dynamics products. There are everybody, in fact, right from the payload data processing to the onboard, everybody needs to know the orbit. And in fact, even the onboard orbit, the control system also needs to know the spacecraft position and velocity for many of its computation. So this is one very important activity that we do in the ground segment for tracking and control. Next. So the next box is about the planning of the telemetry, telecommand, and the payload. So like I said, each satellite might carry different types of payloads, but who is going to plan the payloads? When is it going to be turned on? So these information or the request for the payload comes from the user. The user could be it could be a person in sitting in the defense, or it could be somebody sitting in the agricultural ministry. It could be some user who has paid money or who has entered into an agreement with ISRO to get the satellite image data over a particular region. It could be different types of users. So all these requests for every satellite is consolidated, and then this and based on the request and the feasibility. So there's a feasibility check with respect to the constraints on the satellite, whether the power system will support this kind of an operation, whether the area that the user is requesting is actually accessible to the satellite, even if it's accessible, whether I can maneuver the satellite to look at the area, do I have enough memory in the onboard to store this data, do I have an opportunity to download this data. So all these constraints are checked on the ground before they're actually programmed to the satellite. So once these constraints are met, these activities or this plan is converted from a plan to a set of commands which the satellite will understand. So it is not just turning on the payload, but it's also turning on the data handling system, the solid state recorder, and turning on the downlink system, the RF antennas, and to send this data that is acquired by the payload to the ground station. So this entire activity is called planning for the payload operations. You're also planning for the TTC, that is the next box, which is the scheduling. So, it is a problem of optimization. I have, let us say, 25 satellites today, as we are working with 25, and I have some n number of ground stations. And each ground station would see the satellite probably 4 times or sometimes 8 to 9 times. How do I allocate my resource of a station to a particular satellite? So this job is done by scheduling. So it is not as simple as, giving one station to one satellite. You also need to worry about clashes that occur in the scheduling. So maybe, the station has a capability, the station has a geometric visibility to more than one satellite. Then how do I decide which satellite gets a priority over the station? Sometimes I need to, allocate half the pass, the visibility to one satellite and the other half to another station. So all these are governed by, again, some rules based on how often do I need a satellite to be downlinking data or a telemetry to a ground station. How often, how long can I go without a station support? How often do I need data for my orbit determination? So what happens if there's an anomaly and we do not, if the anomaly has occurred in a non-visibility, and how quickly should we detect the anomaly, and how long can the satellite survive without anyone from ground attending to that anomaly? So all these are rules that are embedded, and based on these rules, the scheduling is done. Looks simple, but believe me, this is an extremely complicated affair. So now, having done all this, we talked about so many things. How does this whole system work when you have so many satellites, so many ground stations, and so many interfaces with so many entities? You have users across the world, you have NRSA giving you some requests, the data has to go to someone else. How does this whole system work? So this whole system is mostly automated. So interfaces across centers, interfaces across entities within our own center mostly are automated, because it's almost impossible for man in loop to be there to carry out all these activities for each and every satellite. So I'll talk a little bit about automation in my future slides. Now let me go further on the analysis part. So having the satellite and having got the telemetry data, having got the payload data, having understood the payload operations, what do we do further? So we also have to carry out analysis on a day-to-day basis, generate a daily report on how the satellite has behaved. Is there a trend of some kind of an anomaly that you see in this analysis? Is there some non-nominal behavior? Is every parameter of the satellite behaving perfectly as it's supposed to be? So all these are things that come out in the analysis. Of late, we also built a lot of tools using AI and ML, which we are using for our daily analysis. And finally, data product management, though it is not done here at this center, it is not just telemetry data, but it's also the image data, the products that we get that need to be disseminated to the various users. So this is done by various other centers, but this image, acquiring the image data or the payload data and disseminating to the users, archiving it, and then, and there are so many things that the data product requires. A meta information of when the product was acquired, what are the lat longs, how do you geocode it, and what was the attitude of the satellite at that point of time, what was the thermal system behavior at that point of time. Many of these things may also be extremely important for the user when he is trying to analyze the satellite data. So these products are also disseminated along with the image data. So that was in brief a very an overview of the entire ground segment. So to further talk to you a little more about spacecraft operations, this is a slide not meant for ground segment operations, but it gives you a fair idea of how the life cycle of a person who works in the mission operations center, what happens during all these activities. So right from getting inputs from the mission design, establishing the ground segment, which I just briefly explained to you, establishing interfaces with various entities that are involved in the ground segment, and also this ground segment is ready much before the satellite is in orbit. So while the satellite is getting tested in the checkout in URO Satellite Center, we simultaneously prepare the ground segment with our own, it could be software, hardware, and we also need to do the checkout of all the software and hardware elements that become a part of the ground segment. So, though I can say that many of our elements conceptually are the same, but every new mission brings in a lot of new elements, even in the ground segment. It could be a different data format, it could be a different type of encryption, it could be a satellite with a different data rate itself, and recently, like we had the SpaceX mission. I'm not sure if all of you saw those videos on the ISRO headquarters website of the docking. This entire video data was first time acquired through the telemetry channel and processed in real time. And as the docking was happening, people were actually watching those videos live. So this was a new element, high data rate data coming through the telemetry, not from the payload or through the payload chain, but coming through the telemetry chain itself and getting processed and getting displayed in real time. So every new mission brings in its challenges. So while the satellite is getting tested on the ground, in the checkout or in the AIT, we also check out the ground segment elements. And then we do something called the pre-launch simulations, wherein the entire network of stations, the entire communication links, um, the entire computer systems, all the hardware and software are exercised as if the data is coming from the satellite. It could be a recorded data or it could be a old data coming from some other satellite, but they are simulated and the entire chain is run during the pre-launch simulations. So then after the pre-launch simulations are successful, we have the launch, and then this center picture, I'm sure all of you have seen a zillion times on TV. This is a picture of a control center from where we control our satellites just as it is injected and while they are in their commissioning phase. So the satellite, while it is in the orbit, we have something called a launch and an early orbit phase, wherein all the systems are commissioned. And we do this activity slowly because every system or every time we do a new operation, we get a feedback for the next operation or a go for the next operation. And from then we go on to a regular commissioning phase wherein we declare that the satellite is healthy, the satellite is commissioned, all the elements that are involved in operating the satellite are working properly, the payloads are working properly, and then from the commissioning phase, we get into the normal phase. So that is what we here at ISTRAC do on a regular basis. We work with the satellites day in and day out and during the normal phase. And from then on, we go to a phase called the decommissioning phase. When the life of the satellite is over, now the decommissioning phase is gaining a lot of importance as we are going through a debris-free space. So when I say debris-free, every space-faring agency is now responsible to bring down the satellite that it puts within a certain period of time. So either it decays naturally if it's in a low Earth orbit, or it should carry some fuel so that it can be brought to a lower orbit, finally from where it can be decommissioned. So this is an important activity that has gained a lot of importance in the last few years. Considering that there is a lot of space debris, we don't want to add more and more debris to what is already there now. Now, I talked a lot about the interfaces that are there in the ground segment. You can see the satellite in the middle, the ops team sitting there controlling the satellite. They will interface with the TTC ground stations. That is, the TTC is the telemetry telecommand network ground stations. They interface with the ISSDC. I'll talk a little bit about that. That is where, that is ISRO's data center, which hosts all the science data that is coming from the Chandrayaan or the Aditya or the Mangalyaan or the Astrosat or the Aditya. So all these satellite data is received at this ISSDC and it is hosted there on a website for people to use it. Then we have the flight dynamics. I already talked a lot about it. Scheduling, talked about it. Of course, everything we do, we always have, constantly are in touch with the ISTRAC management and the ISRO management, and all the guidelines that we get for mission operations comes from the management. Apart from this, we have communication links because you need to link our control center with each of these ground stations which are there around the world. And of course, there's a computer network which is sitting on top of these links to channelize the data to the right systems. In the outer circle, you have the people who designed the satellites, and we take their help every time there is an anomaly and we need some extra information about the satellites that is beyond us. So these are the subsystem designers. We also interface with the defense people because some of the data may be going to them. We interface with the users for the payload planning. We interface with external agencies like JPL, sometimes with stations and agencies which are having their own ground station. We hire ground stations where we don't have our own ground stations. So we could be interfacing with them. And apart from this, the bullet that you see in the air, the extreme left is called the ASSC. We have an alternate spacecraft control center. For some reason, if the control center where I'm sitting right now is not accessible, let's say there's a natural calamity and we are not able to reach, so we can carry our entire operations from the alternate control center because you cannot leave the spaces assets unattended. So we also regularly work with the alternate control center to keep it alive and kicking. So this slide, I think I will skip a little bit because, I'm going to talk a little bit about our ground station. This is the campus where we work. Most part of the ground segment is hosted here, and you can see the image here. I'm not sure if you can see my cursor. This is the mission operations complex, which you mostly see on TV, especially when there is an important spacecraft operations going on. Sorry, this is inside the mission operations complex. And these are some of our stations and our network control center that you see in our campus. So this is again, we have a separate building wherein we conduct the spacecraft operations when the spacecraft is in its initial commissioning phase. And there is another building wherein we take care of our regular on-orbit satellites that have been there. In fact, we have satellites which are, many satellites which are more than 10-year-old. We have satellites which are as old as were launched this year, as young as few months, to satellites which are even more than 15 years old. So this is just a glimpse of our control center. I have about 10 to 15 minutes left in my presentation. So let me just go through. So these are the big screens that you see, which also capture the health or the status of the satellite or the mission operations that are going on. So now, how does this ground station actually track the satellite? So you see in this animation, as the satellite is moving over the horizon of the station, the ground station antenna continuously tracks the satellite and is able to receive data from this satellite. So these ground stations can be all over the world. And the box that you see here in green, or the circle that you see here in green, which is to the right bottom, is the control center. So even though the satellite is passing over a ground station, which may be on the other side of the earth, let's say some station in the US, you will still get the satellite data in real time through a communication link. And this was what I was talking about, the other element that are involved. So we build communication links between the ground station antenna to our control center. So we will have such communication links with each and every station that is there all around the world. And even our control center itself here, where we work or where I'm sitting now, we have about 4 to 5 antennas which are used for tracking various type of satellites. So this is just a small image of how the mission operations take place. Now, how do you decide where to keep your ground station antennas? One of the important things that we do here is to track the launch vehicle. So unlike a satellite which stays in the orbit for days, the launch vehicle's life is, say, about from 15 minutes to max about 20 minutes, wherein you need to get every bit of information from the launch vehicle to understand how it has performed. Because finally, the end of the launch vehicle trajectory, it is going to inject the satellite. It could be one or many that it is carrying. So the trajectory can be, have various shapes and various directions. So let me just tell you, if we were launching a polar satellite, so obviously the launch vehicle trajectory has to come down south. Here you see Sriharikota, our launch pad. So if it is a polar satellite, the launch vehicle has to come down and the trajectory will be down. Now, if the trajectory is going down, I need to have ground stations all along this path, because unlike a satellite, which is there for a long time and I can afford to record the data and play back the data, in the launch vehicle trajectory, we would wish to have every information every second during its trajectory to know how it is performing. So we try to keep our stations along the line of the trajectory, and that is how you see here for a polar satellite. This is the trajectory that you see for a polar satellite launch vehicle. Now, if you have a trajectory that is going eastward, let us say Here I've shown a trajectory for the geostationary satellite. This could be an interplanetary mission, or it could be an inclined orbit satellite, it could be an inclined orbit satellite which is having an inclination of about 20 degrees or 37 degrees. And then you need to place these ground stations all along this trajectory path in order to get the data from the launch vehicle. So next, uh, that is during the launch trajectory. So once you acquired data from the launch vehicle, the next thing is to arrive at stations in order to support your satellite mission. Now, in order to support a satellite mission, let us say I'm having a very important mission like a Mars orbiter mission, wherein I have critical operations all through the day. So 24/7, I need data as the satellite is either approaching its orbit or it's in the coasting phase. So we would like to place our stations all around the world. And here you can see there are some deep space network. I will be also talking about that in the next few minutes. A deep space antenna is an antenna that can receive, it's a huge antenna. Usually for our tracking our low Earth orbits, we need about 10 to 11 meter antenna. But if you're tracking a satellite which is 4 lakh kilometers, like a lunar mission, or if you're tracking something like if you're tracking a Mars mission or a Venus mission, wherein the distance could be as far as 400 million kilometers, you need a deep space antenna. And here in Bangalore, we have a 32-meter antenna. I'll be showing you that. Yeah. So this is a bird's eye view of the campus where we have a 32-meter antenna. You can see the tag D32. This is very much in Bangalore, and this is the data center I was talking about. So this antenna is capable of tracking satellites which are as far as 400 million kilometers. So now, again, coming back, if you have to look at it on a globe, we have stations everywhere. And there are some stations which are extremely important for a polar orbit. They are nothing but these polar stations in Svalbard, which is close to the North Pole, and in Antarctica. So we have our own station in Antarctica too, which is extremely useful, because when you have a polar orbit, these stations will be able to see the satellite almost every orbit. If you have stations on the equator, because of the Earth's rotation, you will get very few passes on these stations in a day. So we talked about this satellite, and this is again a type of the type of antenna systems that we are carrying today. There are different sizes for these antennas, and these antennas, the metric for an antenna is something called the G bar T. So the antenna gain is extremely important, which again depends on the size. So in order to have receive a signal from a farther distance, in order to have a good link margin with a satellite, you need to compute the link margin. And for that, the farther the distance, the bigger the antenna you need to have. So we have different types of antenna. I already told you about the 32-meter antenna. We have the 18-meter antenna, which is tracking Aditya right now, which is at the Lagrange point L1. I'm sure all of you know about Aditya and the Lagrange point. So that is at 15 lakh kilometer. So that is, we are tracking that using the 18-meter, and we have a host of 11-meter antennas. And there's something very interesting about this shipbound terminals, which I just didn't mention. So a mission like Aditya or Mars, they have some geometric constraints which say that the launch vehicle needs to inject the satellite. Usually the launch vehicle will always inject the satellite at the perigee of its injection orbit, and that point cannot be anywhere. It will be governed by the planetary motion and the date and time of launch, and that point of injection sometimes is on a in a no man's land. It could be in the middle of the sea, or it could be at some point which is favorable to geometry but totally inaccessible to a person. So in such cases, if it is in the oceans, we deploy these antennas on a ship, and send the ship sailing to the Pacific or the Atlantic to acquire data from the satellite. So this is another very interesting aspect of our missions. And if it is on an island where we don't have a regular ground station, we send a small transportable terminal to that island temporarily to acquire data from the mission. So this is just a picture of what I just described to you, the shipborne terminal, and you can see that we've sailed number of ships with these antennas for most of our missions, even for the Chandrayaan, even for the Aditya, even for the Mangalyaan, and sometimes it's also required for our GSLVs also. So this is just a picture. I think the rest of my thing is mostly pictures. This is a picture of all the ground stations that we have in Lucknow, Trivandrum, Brunei, and all these stations are automated and they controlled centrally from one single place called the Network Control Center. Then this is a slide on the Indian Space Data Center, wherein all the science data is recorded and stored. And this is again a little bit about Chandrayaan. I wanted to show you about, and I'm sure all of you know about various aspects of the Chandrayaan mission. We had the launch vehicle, we had earthbound orbits, the satellite went around the Earth, got enough energy to go out on a translunar trajectory. It went close to the moon and then we got captured around the moon. It did the lunar burns to come close. And finally, at 30 kilometers from the surface of the moon, we started the automatic landing sequencer. And from there, it landed on the moon. And then there was a rover, a soft landing that is important. It did a soft landing on the moon. And then the rover came out of the belly of the lander and collected enough data, which excited most of us. And the data is still being analyzed by many of the scientists. So this is a profile of what I just described. Let me just skip this. It has a lot of numbers on it. This is the magnificent or the majestic LVM-3 M4, which carried the Chandrayaan. Yeah, so this is what I wanted to show you here. So these were the stations across the world owned by different agencies. The Swedish Space Corporation, the SSC, the ESA is the European Space Agency. So we had hired stations from all these agencies. There was one in Hawaii, Santiago, Kuru in the US, Goonhilly, apart from our own stations in Lucknow, Bangalore, Mauritius, Biak in Indonesia, Brunei, and our own deep space network here in Bangalore to track and control the Chandrayaan. So this was one of the launch trajectory of Chandrayaan was also extremely interesting. It was an eastward bound trajectory. And these are the stations, the location of the stations that I just mentioned to you. Yeah, this is a picture that all of us are very proud about. The day we landed safely on the moon. They say that not all zeros are bad. And we were extremely happy to see zeros here on that particular day in the Mission Operation Control Center. Horizontal velocity 0, vertical velocity 0, and altitude 0. It meant that we had landed softly on the moon. Yeah. So these are some of the pictures of that. And then this is how the rover went all around the moon surface. And this is some of the communication that happened between the rover and the lander. And then this data was again received by our antenna, the deep space antenna in Bailalu in Bangalore. And yeah, this is the Aditya mission, a picture of the Aditya mission that I talked about, which is at L1, which is again tracked by our 18-meter antenna. And for this, the telemetry telecommand is in the X band. So with that, I end. Thank you so much. I could take some questions if you have. Thank you.